Okay. So, this is another part of the fuzzy systems. Actually, this is the next stage, next phase of fuzzy systems. So what we have seen so far. So if you remember the fuzzy system that we looked at is, first of all, we have if-then rules. Yeah. And then, so each member has a degree of belonging based on the membership function. For example, if X has this and then Y is that, and then the output is this. And then we compose all these different rules under one umbrella using different fuzzy systems methods, for example, Mamdani fuzzy system or Tagagi-Sugano fuzzy system. And then you, at the end, once you brought all these fuzzy rules together, and then now you got a defuzzified model. So you got a fuzzified model. Then you need to defuzzified using different methods. It's the center of shape and so on. So basically, a weighted average of the output that gives you a defuzzified model. So what parameters are we dealing with here? So parameters of the membership functions. And if you look at the Mamdani fuzzy model, in both the first part, if part, and the then part, this is where we use membership functions. So we need to find the values of these parameters of these membership functions. The second model, if you look at the Tagagi-Sugano model, so we always look at the first part. This is all about membership functions. So you need to find the values of these parameters of the membership functions, and the output is linear equation, and we need to find the multipliers of these values, basically the constant of the linear equation for each parameter. So how would you determine this? In our examples, we made this up, and you may go to and speak to experts, and you may be able to get their opinion and so on. But this may not be the optimal way of doing this. So if you have a data, and you can construct your initial if-then rules, and then you can use artificial neural networks to learn the values of these parameters, and you may be able to reach optimum values. So that's why Anfis, adaptive neural fuzzy inference system, has been developed. So you have inputs, the values, and then you have output, and then in order to meet your target, the values inside of that system is being learned using backpropagation method, for example. So what are you learning here is the values of the parameter membership functions. So in order to develop this was introduced. This is very much based on the Tagagi-Sugano model, and it is called first order Sugano fuzzy model. For the sake of illustration, we came up with two inputs and two rules here. So you got the data inputs, the variables, X and Y. X has two fuzzy sets or two rules here, and Y similarly two rules, and they this is in the layer one. The values of X are fuzzified. So you need to compose this using AND rule. AND rule in the fuzzy system. How would you be able to describe it using mathematically? Which mathematical form can represent AND operation? So this is where you can use this as a multiplier, and it goes here. And if you come to this last stage, how would you be able to do that? So you need to sum this output, and this output comes from the first rule, and the second one comes from the other one, and then you will get a weighted average here. So this is based on the first order Zagorskian model, and rule 1 and rule 2, and the outputs are represented by linear equation. So falsification and composition of the rules and the falsification based on the weighted average here. So in the first section, and this is something that you can use as to represent each value and membership function here for each fuzzy set. And layer 2 is two-norm operator, which refers to AND operation, and mathematically you can multiply this. So multiplication gives you the minimum. For example, 0.2 and 0.3. If you take the minimum, it's 0.2, but if you multiplied it, it is less than 0.2. It's still minimum. So this is how we can describe it. If you use AND operation, you won't be able to derive the function with respect to x and y. So you need to do it through an equation. Therefore, this is used in the way of mathematical calculation. And then you need to take this to normalized approach, and then this comes to the last for each rule as a defalsification in the layer 4, and the final layer 5. This is a kind of normalized defalsification model. This is where you can get the real life value that can be used in the real life. So how it is being dealt with, or how it is being calculated, the if part of this is called premise part of this nonlinear. This is very much fixed, so you don't change it, but you use a graded descent or backpropagation method to be able to use it. For the consequent part, again, there are two different ways. Either use least square estimator like a linear regression, because it's a linear equation there, or you fix it, and also use signals, node outputs or error signals to be able to find the way. So if you use forward pass method, first the complex part with all these membership functions fixed, don't change the values, but use least square estimator to be able to find the consequent part. So, or if you want to use backward pass, like a backpropagation learning, use gradient descent to be able to learn the values of the parameters of the membership function, like triangular membership function, and fix the values of the linear equation at the consequent part in the last part, after the then part. So this is how it can be done. And in terms of gradient descent method for adaptive neural fuzzy inference system, it's like a learning based on the error between the actual output and the error, the output that was produced by your model. And you need to take the gradient of this and based on the learning rate, and it can be trained that way. So let's assume that we have a trained model, and now we modeled a sync equation that way. The x values between -1 and 10, and we have 4 different membership functions, and we have 16 rules. So now this is an initial membership function that we set initially. So 4 membership functions, basically 4 sets here, and between -1 and 10, so equally distributed. But after you learn this using gradient descent method, after 10 cycles, 10 epochs, so what you can see that actually it's changed. So it means that the way you train helps the system to learn the values of the parameters of your membership function. In fact, if you look at this one, you can only need 3 membership functions, and you may not need the 4th membership function here, for example. So you can see that how it adjusts into the error and makes a perfect system. Again, the error is getting down to as you progress as you train more. So let's say we calculate and we finished another example here, and we come up with membership functions here for 2 different sets of rules, and we'll make the calculation. And this is just illustration, just an example to be able to show you how the system can be used to give you an output. So there is no training. We assume that the training has been done and we got these values perfectly fit into the system, and we'll just show you how fuzzy inference system makes the calculation at the end to give you a real value. So let's assume that these are the membership functions we got for the first rule and the second rule for parameters x and y, and this is the if part of this connected with end, and then part of this, because this is the first order Sugano model, so it the output is defined by using members linear equation here. So let's say we are giving values for x3 and y4, and we are asked to find the output of this. So what would be the output? So let's say we have 2 membership functions, as we said, for a1 and a2 for x, and b1 and b2 for y. So the input for x is 3. So we make the calculation here for x 0.1 and 0.5, and for y4 b1 and b2. Let's have a look at which ones are going to be fired based on the if-then rules. So x3 a2 and y4 is b2, because this is in the rule. If x is a2 and y is b2, then you make the calculation. So for this one, the value of this is 0.1, as you can see, and 0.5, and again and this way. If you look at this one, if a2 is 0.1, b2 is 0.039, you can see that x3 a2 is 0.1 and b2 is 0.03 here. And then you need to take the minimum if you were applying a traditional one, but for the Tagagi's Anfis adaptive neurofuzzy system, you need to multiply this to apply the minimum operator, the AND operator, and then you'll get this one, and this will go here. And again, if you, and then for the first rule, if you look at this one, A1 is for 0.5 and B1 is 0.5, as you can see here, 0.5, 0.5. Basically, what you need to do, you need to take the minimum 0.5, and you need to take the minimum 0.035, and you need to take the average. So this is what we are doing here. But we need to multiply this. So this comes here is 0.05, and this 0.039. Now you need to normalize it to be able to find the normalized value output of this. So normalized value is this one and this one. So what is interesting here is that you will be able to see which rule is dominant here, or which parameter is dominant here. So when you normalize it, for example, it comes here, and this is going to dominate the outcome here. For example, the reason is that the weight is going to be different. The weight is going to be used to fire the output here, the equation here. So it means that the first rule is going to be having a higher degree of influence, whereas if you look at the second one, is going to be having less influence in the decision making. At the end of this calculation, you will be able to see if you have multiple rules, for example, hundreds of rules, in order to avoid computational complexity, you may be able to identify which rules have less than, let's say, you can put a threshold less than 0.01 weight here, then you can get rid of these and you can simplify the calculation because these are not going to affect the output that much. And then finally, the falsification is coming here, and you need to put this together to make a decision, and you can get the real data. So this is how you can make the calculation by using an Anfis model that has already been trained. So again, if you don't use the multiplication but use AND operation, what is going to happen? So here, if you use minimum here, you will get this 0.05 and 0.5. If you again normalize it, actually nothing is going to change that much because the first rule has still a larger influence, whereas the second rule has less influence. But again, this multiplied by the first and the second rule, and then finally you will get your result. So the result has changed, of course, because by multiplication in the AND operation will give you much less result. But again, if you are trying to assess the influence of rules, have not changed, then you will be able to assess your rule base. So this is another good thing that you can see as an analysis of just before the falsification method. This is where you normalize it, and this way will give you further information about your rule base. Of course, the values are going to be optimized right at the end by putting a threshold. As you learn, you will be able to get rid of some of the rules here. So so two things here. The first one is the influence of the rules can be determined in this way, regardless of multiplier or AND operation you use, because the order of the rules have not changed. The influence of the rules have not changed. As you can see here, for example, and there's a significant difference between the weights here, the influence of the rules for the model where you use minimum instead of multiplier. And if you go back and have a look at the model that you use where multiplier was used, again, the influence of these rules, the order has not changed. There is still a significant difference between them. But of course, because the multiplier are going to change, therefore the output is going to be changed. But this model cannot be used in such cases where adaptivity is applied, because you need to derive the function with respect to x, gradient descent. But I just want to show you to understand that it is possible, but there is a difference. So this is where gradient descent is applied, or this is where you need to apply backpropagation, or different training algorithms is applied. So you need to use this multiplier, the equation, to be able to apply the derivation concept in mathematics to this type of equation. So, but one way or another, as the system learns and finds the error between the actual output and the computed output, is try to fix the error and minimize the root mean square error to fit the data into a model. In these cases, for example, we use this membership function. You may change this membership function in different ways. You can come up with different membership functions, but one way or another, we showed that as you learn, although you set these values and membership functions in this way at the beginning as the initial set, after you learned, the values of these parameters change in order to fit data into your model. So this is a clever way of building your membership function and also rule base. And based on this, if you find that one of these membership functions are not playing a major role, you can remove it. Even based on this, you can do the analysis to remove some of the rules to reduce the computational complexity. So then finally, I think I just want to show you the first picture that I showed you. Now we have data-driven models. Now we have a model that could be further augmented by human experts. So if you talk to the experts and if you bring the rules on board, you can use both data-driven rules and human expert rules together and then put it into one pool and use it. And based on the analysis and gradation model or backpropagation model, then you will be able to optimize the rule that have been proposed by humans as well. So actually you benefit from the rules that have been proposed by the humans, but what you could do, you can just adjust the values that have provided you with. And of course, and you may be able to try these two separately or together, and you can come up with a final model where data-driven model and human expertise are combined together to develop a model. Actually, for example, human expertise is particularly important is to understand the historical architecture because this is where data is not there. But for certain cases, there may be a sensor data being collected. So sensor data and modeled by using data-driven if-then rules, and the historical information from architectures or historians could be used to develop human expertise based if-then rules, and you can use both to come up with an interesting applications. So I think now this is up to you to develop such systems and make it work.